afternoon, ladies and gentlemen. My name is Ibrahim Ali Aliyu from the Department of Business Administration, University of Abuja. I'm here to continue what we've started first semester, which is Analysis for Business Decision 2. The first semester is Analysis for Business Decision 1, which we examine some foundational model of quantitative techniques and their application to business. However, this semester, we'll be examining the continuation of first semester modules. As we can see, the objective of this study is to equip students with the requisite quantitative techniques to aid them in taking future managerial decisions in their various areas, future areas of endeavor. And the outline for this semester composed of 5 modules. 5 study sessions. Study session 1 addresses the assignment model, which we shall be treating today. Then we'll follow it up with transportation model, then Markov analysis, queuing model. Then we cap it up with linear programming model. With particularly, we'll be looking at simplex method because the first semester we examine the graphical approach to linear programming. So this semester we'll be examining simplex algorithm. We'll examine the maximization, the minimization, as well as the mixed constraints. But the study session of today is our study session 1, which is assignment model. An assignment model, as we can see, simply it's one of the optimization tools that management experts use in making managerial decisions. Assignment model, we come across it in our daily, day-to-day office or industrial routine, such as determining the most efficient way to assign people to project or task. And the basic objective of assignment model is to minimize cost or time of performing a task at hand or maximize sales or revenue. When we say optimization, what we mean is simple. We maximize benefits and we minimize costs. As we can see, there are various variants of assignment model. We have the minimization problem, we have the maximization problem, we have the unbalanced assignment problem, and we have the what? Assignment problem with restriction. But for sake of our study, we'll focus on maximization and what? Minimization. And as we can see, the following are the application of assignment model: assigning employee to various machines, effectiveness of teachers to subjects, salesmen to different sales area. How do we how do we assign various teller in banks to various counters? In what way can we assign them, either to maximize earning or to minimize cost? We shall be seeing. There are various methods of solving assignment model, but for purpose of this our study session, we'll be basing on the Hungarian method, which is the assignment model that follows a similar pattern close to that of linear programming. We should also bear in mind that assignment model is a variant of transportation model, which happens to be the variant of linear programming. So assignment model is an extension of linear programming. And the following are the steps of solving assignment model. Whenever you are given any typical assignment model, maybe like the one on the board, you examine the dimension or the order of the assignment model. This is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is 5 by 5. It's of equal dimension. So there is no need to add dummy variable. Assuming we have F here with values, it means that the numbers of row exceeded the number of column. So we need to add a dummy column here and code the dummy. We allocate zeros to each of the dummy. So having established the order of the assignment model, if the problem is minimization, what do? We simply look for the smallest number in each row, row-wise, then we subtract each number from all, we subtract the smallest number from all the numbers in each row. We do that for all the rows. That will give us what we call row opportunity cost table. Then, from row opportunity cost table, let me illustrate this further by looking at this minimization problem. And the minimization problem has this following matrix, as can be seen on the screen. And what we can see is we have 5 companies and 5 contracts, A to D. For sake of analysis, I shorten the zeros, remove 3 zeros. This is 45,000, 50, 60, 30, 60,000. Now, this is a typical minimization problem. Question A is which bid should be given should X and Y company accept in order to fulfill the contract terms at least cost, and what is the total cost of the subcontract? Now, what do we need to do? Since this is minimization, even without being told that it's minimization, once you see cost, once you see time, the objective of that is to minimize. But once you see sales or revenue, without being told, students, you should understand the objective there is to maximize. Both minimization and maximization are all subsets of optimization. And bearing in mind, assignment model overall objective is to optimize. That is efficient allocation of resources in such a way that we maximize benefit and we minimize cost. And now back to the subject of that is at hand in our first example. If you look critically, since this is minimization, we first of all examine the order. Is there need for dummy? As I stated earlier, there is no need for dummy, because as you can see, it has 5 rows and what? 5 columns. Then what is the next thing? We proceed to what we call the row opportunity cost table. How do we derive row opportunity cost table? We simply look for the least number, the smallest number in the entire table. Sorry, in the entire row. Let's pick row A, for instance, which is the smallest number. The smallest number as far as this row is concerned is 30. And subtracting 30 away from each and every element here, what do we have? We have what we have in our next slide there, which is the row opportunity cost table. As you can see, 30 removed from this gives us 15, as can be seen from the table in V, as highlighted by my red marker. Also, 30 removed from 60 give us 30. 30 removed from 75 give us this. Let's take a look at column C, for instance. If you look at column C, the smallest number in column C is 40. So 40 removed from 60 will give us 20, as highlighted in column C. So that's how we arrive at the new table we term as row opportunity cost table. As far as assignment model is concerned, you look for every smallest number. Check the previous table. For instance, the previous table, the smallest number each on each row wise, then you subtract that smallest number from each row correspondingly. That will give us this table termed as row opportunity cost table. That is step number 2. Haven't done your row opportunity cost table, then you now operationalize using that same table column wise. Now you operationalize that table column wise. For instance, look at V column. Which smallest number are we having there? If you examine it critically, I think we are having 10,000 in V column. So if you subtract 10,000 from everything, meaning V column, our next value should be 5, 0, 10, 0, and what? 25. Let's see what we have. You see, it's exactly as predicted. If you look at our previous column, which is our V column, if you examine it very well, in our row opportunity cost, the smallest number here is 0. Subtracting 0 from the entirety results in the same value. Similarly, X also is 0. Let me move to the next table. You see, we just repeat the entirety of what is in the W column and the X column, because the smallest number there is 0. Let's go back to the previous table and look at the Y column. In the Y column, what do we have? We have numbers without 0. What is the smallest number there? As far as my eye can see, is 35,000, plainly highlighted. Then what do we need to do? Pick that 35,000, subtract it entirely from that column. We have what we have in the next table. So this gives us what we call column opportunity cost table. Now, whenever you are through with both row and column opportunity cost table, the next step is what we call testing for optimality, which is step 4. How do you test for optimality? You rule straight line to cover as many zeros as possible. Ruling straight line to cover as many zeros as possible, we point to something. How do we know we've arrived at the optimal solution? When the numbers of straight line rule throughout the table equate the dimension or the order of the table. This is 5 by 5. So the number of straight line has to be 5. If it is not up to 5, we have to proceed to step 5, which we call the revised table, which I will guide you on how to do. So let's try and see how to rule our straight line. For instance, if you look at the V column, ruling V column we cancel to 0, ruling W column we cancel to 0, X column will cancel 1, Y column will cancel 1, Z column will cancel 2. Similarly, if I look at row wise, I will cancel 1 in A column, 2 in B column, 1 in C column, D column 3, E column 1. You can see the highest number of 0 I can cancel is in D column. So I will rule my first line passing through the D column. That will cancel 3, 0. So if you check the subsequent table, you will notice the ruling. The first line there is what? D, because it cancels 3 zeros. You have to make sure you rule tactically. If not, you will arrive at 5 numbers of straight line, whereas your solution will be what? Suboptimal. Now, having cancelled 3, 0, or I will better say, let me illustrate it this way. Let me reproduce what is on the screen on the board. If you journey down with me with what I'm having here, I'm going to put the figures, the cost figures. I'm going to put the cost figures in red, and I will use black to rule. The V column, we have 5,000, 0, 10, we have 0, and we have 25. The next one, we have 30, 15, 30, 0, 0. The X column, we have 45, 0, 40, 40, 40. Then we have 35, the Y. We have 25, we have 35, we have 0, and we have 125. Then the Z column, 0, 5, 0, 5, and 10. Now, here is what I'm trying to illustrate earlier. If we observe critically, we discover that ruling this way, column-wise, we cancel 2, 0, 2, 0, 1, 0, 1, 0, 2, 0. Here, 1, 0, 2, 0, 2, 0, 3, 1. So it is better to cancel the 3 zeros first, because the objective of ruling the straight line is to eliminate as many zeros as are possible. If we look again, how do we cancel the zeros again? Ruling this way also, we cancel 2 zeros. Are we together, class? Then also ruling this way, we cancel how many zero? 2. Ruling this way also, we cancel how many zero? 2. So how many numbers of straight line we have? 1, 2, 3, 4. But the dimension of the cost matrix is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Meaning that the solution is not yet optimal. We move to what we call step 6. If you look critically on the screen, what we have there is what we reproduce on the board. We only use the board for clear illustration and to deepen understanding. How do we move to the revised table, and why are we moving to the revised table? We are simply moving to the revised table simply because the number of straight lines that we have, as highlighted on the screen, 1, 2, 3, 4, is not equal to the dimension of the matrix. So there is need to revise the table. And how do we revise the table? We simply look for the smallest number not covered by the straight line entirely. The straight lines cover some set of numbers. We are to leave them untouched. So the smallest number not covered by the straight line, examining carefully, if we look, we have 35, 35, 125, we have 25, we have 10, 5. The smallest number not covered by the straight line is 5,000. If we examine it carefully, then we pick that 5,000 and subtract it from all these numbers not covered by the straight line. Then anywhere two lines intersect, we add that very particular 5,000. For instance, this is 5, which is the smallest of the entire table. 5,000. Bear with me, this is the revised table. We have V, W, X, Y, and Z. The smallest number not covered by the straight line is 5. We subtract 5 from all these numbers not covered by the straight line. 5 minus 5, 0. 0 is covered by the straight line. If you remove 5, 5. Are we together, class? 0 is covered. Then this is 20. 30 is covered. You leave it alone. 15 is point of intersection. What do we say? You add that number to point of intersection. This becomes 20. 30 is covered. Then this 0 transmutate to 5 because it's point of intersection. This one remains 0 because it's covered. Similarly, you remove 5 from here. 40. 0 is covered. 35. 40 because it's covered. Then here is what? 35. Here is what? 30. 25 remain because it's covered. 30 will less 5, it will remain what? 35 will less 5, it will remain 30. 0 is covered. 125 becomes what? 120. Similarly, since all here are covered, we repeat them except for the point of intersection. So the 5 becomes 10. 0 is covered. The 5 becomes 10. Then 10 also remains 10. With this, then we rule our lines to confirm whether it is now optimal or not. How do we know it is optimal? We can only establish optimality if the number of straight line rule equates the dimension, that is, the dimension, the row and column wise of the matrix given. If I rule this way, 2, 2, 1, 2, 1. But this way, 3, 1, 1, 1, 2. So it is preferable to rule this way. Are we together, class? Ruling this way, 2. Are we together, class? Then ruling this way. Are we together? Then ruling this way, making 4. So I can also rule this way, or I rule this way. How many numbers of lines do we have? 1, 2, 3, 4, 5. We have 5 numbers of a straight line, which shows that the solution is equals to the number of dimension of the matrix, which indicate that it is what? Optimal. As you can see, if we move to the final numbers of straight line, you can see them there that the revised cost table, which is exactly what we reproduce on the board, removing 3 zeros, is optimal. Then from this, we go to the final assignment. And now students do find it difficult in operationalizing the final assignment. How do you do the final assignment? You assign to where there is only 1 0. Start by looking column wise. By looking row wise, I want you to understand. Let me illustrate this on the board. Let me put it here. Final assignment. We have A, B, C, D, and E. How do we assign? We begin by assigning to where we have 1 0. If we look at A row, we have 2. B row, 2. C row, 1. It means that C is picking up Z. Contract C should be assigned to contractor Z. Are we together? D is having 2. E is having 1. Contract E should be given to contractor W. There is now a fundamental rule in assigning. In assigning, when you give a job to a particular person or to a particular thing, when you assign a task to a particular person or thing, that task can never be assigned to another person. With that principle, giving C to Z has cancelled this 0. Cancelling this, A is left with V. A is left with 1, which is V. So A is taking what? V. By A taking V, it has cancelled this 0. So B is left with what? X. Class, are you following the elimination process? Then, if you look at it critically, this 0 has also been cancelled since it has been given to A. So D is left with what? Y. Then we go to the original cost matrix. When we go to the original cost matrix, we now see that what we have, let me take you there, the original cost matrix from where we started. A should be given according to what we have on the board. A should be given V. What do we have on V? 45. Original cost matrix, please. B should be given X. What do we have? B to X, we have 40. C should be given Y. What do we have? C to Y, we have 110. Then D should be given Z. What do we have in Z? 25. Then finally, E should be given W. What do we have in W? 25. And that is exactly what we have at the end of this exercise, at the end of step 8. We have 205,000. That represents the minimum cost assignable in contracting. This is the optimal solution. As you can see, A to V, B to X, C to Z, D to Y, E to W eventually give us 205,000. You can see the objective is to minimize cost, and we agree that the minimum cost is 205,000. Then let's look at maximization case. In maximization, which is similar to minimization, the maximization problem is of no problem once you understand minimization. Why do I say so? Simply because maximization only has a step that differs from minimization. Let's see this illustration. How do you treat this illustration? Let's look typically to the illustration we have here. The one we have here is maximization problem. How do we convert this problem to minimization, which is our example 2? Before we can convert this into minimization, what we need to do is look at the entire matrix. The entire matrix of the values given. If we examine it, we identify the highest value. And if you look at it critically, 22 is leading here, 22 is still leading, 22 is still leading, 22 led. So you can see throughout, 22 is the highest value. Then we subtract 22 away from everything away from 22. Then we get a new matrix called the opportunity matrix, as highlighted on the screen there. What you have there is the opportunity cost matrix. What is opportunity cost matrix? It's a polished matrix transformed from maximization problem to minimization. How? We look for the highest value in the entire matrix table, which is 22. Then we subtract 22 away from all the values in the cost matrix, which will result in the value we have on the screen, which is our opportunity cost table. You can see X to A is where the 22 is the only one, 0. From this point, you proceed as if it's minimization. How? The next step is to find what we call row opportunity cost table. What is the row opportunity cost table? Look for the smallest number in the entire row. If you check the first row here, the smallest number is 2. Subtracting 2 from X row will have 14, 8, 0, and 8. Let's check. That is exactly what we have, 14, 8, 0, and 8. So you perform the same operation all through. All through you perform the same operation. If you look at Z, for instance, the smallest number there is 2. Subtracting 2 will be 4, 12, 8, 0. And let's see the next table. Exactly what we have. You can see you've learned that previously in your minimization problem. Then this row opportunity cost table is what you are still going to use just as a minimization to proceed to column opportunity cost. So look column wise as highlighted. Column A, the smallest number is 0. Subtracting 0 from everything will give us column opportunity cost of, if you look at the A column, which is what? The same value. If you look at B, the smallest value there is 2. What do? You pick the 2, subtract the 2 from the entire number. 8 minus 2 will give us 6. 4 minus 2 will give us 2. You can see it in the next table subsequently. The same operation should be carried out column wise. Then we have the column opportunity cost table. Then in the column opportunity cost table, what do? You rule. And in ruling, this here, the solution is optimal because the ruling results in 4 straight lines which tallies with the dimension of 4 by what? 4 matrix given. So the solution here is optimal. There is no need for the revised table. Why there is no need for revised table is because the number of straight line ruled is equals to the numbers of rows and what? Column. So from this, we can carry out what we call our optimal assignment. Optimal assignment, that is to say, the final assignment. How do we assign? I advise you to follow the steps we used earlier in our minimization. What do? You look for the row that has 1. And examining W row, it has 1. So assign to where there is the 0, WC. You can see in the assignment, that is what we have. If C is given to W, nothing can take C again. You cancel all the 0, if any, in that column. Similarly, you go to W. W, we also have 1, which is, sorry, X, we have 1, which is XA. As you can see, that is exactly what we have. Similarly, also, you go to Y row. If you look at the Y row, we have 2. So you leave that for now. But because you are giving X to A, then you must cancel this 0 that is on YA. So Y is left with only what? C. C also had been given. If I'm not mistaken, is that 0 or 6? Not sure yet. So Y should be given to B. Since it has 3 0, this one is cancelled because it has been given to A. It has been given to X. This one is cancelled because it has been given to W. So these 2 zeros are cancelled. It's only remaining the mid 0. That is why Y is taking B. Then finally, Z has only 1, which is D. So Z should be assigned to D. Where do we get this profit figure? We go to the original matrix. Remember, we say WC, right? If you check here, our WC is 20. That's how you see the 20 on that screen. If you check, we say XA. XA is 22. That's how you are seeing the 22 there. Correspondingly, you picked everything. Then we sum. The total maximum profit is what? 78. Then we may have a situation where you have what we call some unbalanced assignment problem. Some unbalanced assignment problem is, for instance, let me make these unbalanced. Let me show you this. Let me make this unbalanced. Assuming I decide to add E here, maybe 10, 16, 20, 18. 1, 2, 3, 4, 5. 1, 2, 3, 4. So this is unbalanced. What do you do, student? You simply add dummy here and put 0, 0, 0, 0, 0. And proceed. If it is maximization, if it is minimization, you proceed accordingly. There are some instances where it might not be dummy row, where it might be dummy column. Just use your intuition and balance from beginning. Introducing a dummy shouldn't cause problem. It doesn't affect the solution. You treat the solution the way you've been taught. So in a nutshell, the assignment problem, what has it taught us? It has taught us one fundamental fact: the process or how to optimally assign things or people to various tasks in such a way that we minimize costs and maximize revenue. So on the backdrop of this, we can see that the summary of what we've learned so far, we've explained the concept of assignment model, we've looked at the various applications of assignment model that involve efficient allocation of things or people to various tasks or projects. So in our next class, we shall be considering what we call transportation model. Then we'll move to what? Queuing. We move to queuing model, Markov analysis. Then we cap it up with what? Which is linear programming, the simplex method. So I will take us to the first part of how we began this. We said assignment model. That is what we have. Look at the various steps. We look at the Hungarian model. Then we look at the various types of assignment model. Then eventually we cap it up. That is the end of study session 1. Also, in order to remind you, these are the course outline for this semester. As can be seen, assignment model is cancelled. So we shall be proceeding to transportation model, which is our next class, which will be our study session 2. Thank you and God bless. I would like to submit the entire lecture in the name of God, the most gracious, the most merciful. Thank you.